Alright, so we're going to look at problem 69 that's in section 3. And this deals with finding the volume of a box that's made from a flat piece of cardboard. And so let's look at what this problem's asking here. And we're going to draw a picture. A lot of times when we're doing something with a geometry, drawing a picture is good. So let me get this out of the way here for a second. So volume of a box. A rectangular sheet of cardboard is to be used in construction of a box by cutting out squares of side length x from each corner and turning up the sides. Suppose the dimensions of the original rectangle are 15 inches by 8 inches. Determine a polynomial on x that would give the volume of the box. Now, so we're dealing with a geometry problem that's specifically looking for volume of a box. And a rectangular box is what we have here. Now, I don't always have all the geometry equations memorized, but if you flip to the front of the book, it will have a rectangular box, and it says V equals LWH. And so we need to find a length, width, and a height for the box we're moving. But we're not starting fully with the box, we're starting with a piece of cardboard. So let's draw a flat piece of cardboard here. I'll give it a width. Match this over here so I have enough room that we can see what's going on. There we go. There's a width on either side. Let's try to give it a length now. Right. So drawing my little piece of cardboard here that we're going to turn into a box. And up here. I'll just tidy up my edges here a bit. There we go. Good. My lines went over. Yeah, I was the kid that the crayons never stayed in the lines. We can tell this by my handwriting. But this should get us started. And so it says the original cardboard is 15 by 8 inches. But we're cutting it. We're cutting a square out of each corner. Let's cut that there and cut this here. And so these squares have sides of x. And so I have a little picture that's kind of giving me an idea of what's going on. And you can do this with your piece of paper, right? You can cut out the corners. And if you cut out the corners, you can fold it up and tape it in, and you get a little box. So what we're going to do here is we're going to look at the geometry that's left behind from this. So one of the first things I want to do is see what it means to cut out a side. And so we're cutting out, taking out, removing, right? And so that suggests subtraction, all right? And so if we have 8 and I'm cutting out an x and I'm cutting out another x, well, I will say that my width is that 8th minus an x minus another x. But we simplify this. We'll say it's 8 minus 2x. And we can do the same thing with the length. The length starts with 15. And I cut out 2 x's. Well, it's gotten me 2 of the variables here that I need. Well, how high is this box going to be? And if I fold this bit up, it sticks straight up. And it has a height of x. And so that's what we're looking for. And so we're going to have a height of x. And so we'll substitute all of these into the volume equation. So I'm substituting, so I'm going to keep my parentheses. So L is 15 minus 2x. W is 8 minus 2x. And H is lowly load x on its own here. And really, I can now kind of mentally scroll to this and treat this as if it's a problem out of the book, right? We've now mapped reality into our mathematics, and we don't have to think about reality anymore. We'll let the math do the work for us. And so what I want to do here is, well, I'm going to FOIL this first part here. So foiling this gives me 120 minus 30x minus 16x plus 4x squared and I still have this lonely x sitting on the outside. Now what I'll do is I'll distribute this x to every term. 120x minus 30x squared minus 16x squared. This x is going to each term. So then we had x coming all the way out here to here. Just put it into there. And for the last term, plus 4x cubed. But this is what we've been doing, right? The only difference with the word problem is this directly maps back to something in reality. We've been multiplying polynomials like this with them not meaning anything directly in reality, but now the words have mapped it to something in reality. And so we'll write the volume, and I'll use descending order. All right, so 4x cubed. I'll gather my like terms, minus 46x squared plus 120x. Now, I had a brother-in-law, and this is actually what he did for a living, very successfully in semi-executive level for Coach and Michael Kors, and the factories that cut the leather to make purses and bags. Just one of the things you had to do is you have to make sure that you're not wasting so much material. And so you would figure out what shape and how to cut the leather so as not to waste bits. And it's based off of ideas like this. You cut a little bit out, how much volume do you get of the final product? It changes with the geometry you're using, but these ideas do get mapped. And he made a good living out of that, and lived in China for a while doing that, and owns a lot of property in England to doing it because he did it rather successfully on a level that was seen as beneficial to these big companies that make things. And so knowing a little bit of mathematical language and how to apply it is the start of what you can then do later on. And mathematics does sneak up on everything. So you wouldn't think making a purse had a purse or a tote bag had a mathematical side to it. But when you want to conserve every piece of product you're using, it actually does become important. And this math skill is the beginning of adding that to your tool set no matter what you're doing.